sketch the function 5x minus 5 over x squared, we will use the derivatives to analyze the function, including the first and the second derivative, and of course the function itself. First, we need to write for the function, we need to find the domain, the intercepts, and asymptotes. The domain, this is a rational function, so the denominator cannot equal to 0. So x squared cannot equal to 0. So x cannot equal to 0. If we write the domain, it will be from negative infinity to 0, and then from 0 to infinity. Right. So that is the domain. The intercepts, there will be the x-intercept and the y-intercept. The x-intercept is where the y equal to 0 and y equal to 0, meaning the whole function equal to 0. So rational function equal to 0, that means the denominator, the numerator, the top equal to 0. So if x equal to 1, so we have the x-intercept x equal to 1 and y equal to 0. Y-intercept is where x equal to 0, but we cannot have x equal to 0, so there's no y-intercept. Because x not equal to 0, so we have no y-intercept. Next, the asymptotes. On this one, we will have the vertical and the horizontal asymptote. So for the vertical asymptote, the vertical asymptote is where the function is undefined because the vertical asymptote is not part of the graph. It happens when the function is undefined. So that undefined where the denominator equal to 0 and numerator not equal to 0. So the denominator equal to 0, bottom equal to 0, x squared equal to 0, give us x equal to 0. Now just make sure that the top is not equal to 0. So when x equal to 0, the top, we put 0 in for x, and that is not equal to 0, so which is good. So we have the vertical asymptote at x equal to 0. Horizontal asymptote is where the limit when x go to infinity or negative infinity. On this one, we only need to do one of them. I choose x goes to infinity of 5x minus 5 over x squared. Uh, since x go to infinity, 5x minus 5, the minus 5 doesn't really do anything because 5 times infinity is a lot bigger than negative 5. So only the one with the highest power matters. And we reduce that when x go to infinity, we just have 5 over x. Now the top is 5, the bottom just getting bigger and bigger. The bigger the denominator, the smaller the quotient. Eventually this go to 0. So we have y equal to 0 is the horizontal asymptote. Next we go to the derivative. To find the derivative, I will write the function so it's easier to take derivative instead of use the quotient rule. First, I will split the top, split the numerator. 5x over x squared cancel to just 5 over x, and 5 over x squared. So we have the x at the bottom move to the top, and then x squared at the bottom move to the top as well. And that is the function. I will rewrite the function here before we take derivative. So the function is 5x to negative 1 minus 5x to negative 2. Right. Now we focus on the derivative. Taking the derivative, just the power rule, we have negative 5x to negative 2 plus 10x to negative 3, and the negative powers move to the bottom, becomes positive. So I have negative 5 on the top over x squared at the bottom plus 10 over x cubed. I need to combine this into one big fraction. It will be easier to solve for the critical point or the partition numbers. So I multiply x on the top, x at the bottom. So the bottom we have x cubed, the common denominator. On the top we have negative 5x plus 10. Right, so that is the derivative. Now, to find the partition numbers, we will consider the case where the function, when the derivative equal to 0 or when it does not exist. Equal to 0 for fraction is where the top equal to 0. Does not exist where the bottom is 0. Right. So the top equal to 0, negative 5x plus 10 equal to 0. So we have x equal to 2. The bottom x cubed equal to 0 when x equal to 0. So let's summary, write a summary here. Partition number x equal to 0, x equal to 2. Now let's find the critical number. Critical number is where the function have to be defined. So critical numbers. For that, we will evaluate the function at 2 and the function at 0. Right. So when x equal to 2, I'll use a calculator here. Y equal 2, enter the function 5x to the negative 1. I should say negative 1 minus 5x to the negative 2. And then we need the values of the function at 2 and 0, so we can hit second graph, and at 0 it is undefined. Move to the right side a little bit, and at 0 it does not exist or it's undefined. At 2 it is equal to 1.25. This is one way to do it. The other way, we hit y variables, y1, and evaluate at 2. So we can convert to fraction 5 over 4 So the function is defined when x equal to 2. Therefore, we have critical numbers only at critical number, only one of them, it at x equal to 2. X equal to 0 does not exist. Right, now we put this information onto the sign chart. Partition numbers, we have x equal to 0 and x equal to 2. So we have 0 and then 2. We need a number line here. So there's a number line. Go from negative infinity to infinity. And this are called partition number. It will divide the number line into intervals, into three intervals. On the left, the middle, and on the right. We will choose a test point in each of the interval. So those are the test point, and the test point we have to test with the derivative. We should write the derivative here. That is negative 5x to negative 2 plus 10x to negative 3. Right. I also use the calculator for this one. Right. Now we have to enter the derivative, negative 5x to the negative 2 plus 10x to the negative 3, and then find the values. When x equal to 0, as obviously it's undefined, but negative 1, it is negative. 1, it is positive, and 3, it is negative. Right? So that is the derivative. Now, if it is the derivative is negative, the function is decreasing. If it is positive, the function is increasing, and negative is decreasing. Furthermore, we have one critical point, x equal to 2, and at x equal to 2, the sign does go from positive to negative, meaning increasing or decreasing. And so based on the sign chart, this have to be the maximum. And we know the maximum value is equal to 5 over 4. So to summarize those information, the function is increasing on 0 to 2 and decreasing on negative infinity to 0, negative infinity to 0, and from 2 to infinity. Local maximum, there is a maximum at x equal to 2. The function value is equal to 5 over 4. And that is the only point we have. There's no minimum, so we have none. So no minimum. Right. Now we go to the second derivative. And we do pretty much the same thing as what we have for the first derivative. Right. So let me turn into two-page mode. And let me copy the first derivative, and then we continue. So the first derivative is negative 5x, negative 2 plus 10x to negative 3. That's what we have for the derivative. Now we check the second derivative, and we go from there. Right, so that is the derivative. Now we take the second derivative. That will be 10x to the negative 3 and minus 30 x to the negative 4 right? And the negative exponent bring to the bottom, we have 10 over x cubed minus 30 over x to the fourth. And we can multiply 1x on the top, 1x at the bottom. So we will have x to the 4 at the bottom, the top 10x minus 30. Right, so that is the second derivative. We will let the second derivative equal to 0 for a fraction. That means the top is 0 and the second derivative does not exist, meaning the denominator, the bottom, equal to 0. So we have 10x minus 30, that is the top equal to 0, so x equal to 3, the bottom equal to 0. So we have x equal to 0. Right. Just like the first derivative, we find the values of the function at those points, because those points could be potentially be an inflection point, or could still be undefined. But we're going to use the function 5x minus 5 divided by x squared, and we look like we have those values. Sorry, variable y variable function y1. Let's evaluate at 0. Right, cannot do that because divided by 0 is undefined. Right, that's okay. Now let's evaluate at 3. Convert to fraction, 10 over 9. So f of 3, 10 over 9. The values of the function at 0 does not exist or undefined. Right. The partition numbers will be x equal to 0 and x equal to 3. So we have x equal to 0 and x equal to 3, which divide the number line, and then the number line. Right. We choose the test point in between the intervals, that are divided by the partition numbers. So we have the left, the middle, and on the right. On the left, we can choose -1. On the middle, we can choose 2. And on the right, we can choose 4. Right? And then we put in the second derivative. We write the second derivative here is 10x to the -3 minus 30 x to the -4. Right? Now we need the second derivative. 10x to the -3 minus 30 x to the -4. Let's go to the table. Second graph. At -1, it is negative. At 2, it is negative. And at 4, it is positive. Right? And the second derivative will give us the concavity. If it's negative, it concave down. If it's positive, it concave up. And where it changes concavity and the function is defined. So when x equal to 3, the function is defined and the concavity change from negative to positive. So there is an inflection point here. Let's summarize this information. The function is concave upward from 3 to infinity, and concave down from negative infinity to 0, and from 0 to 3. We don't write negative infinity to 3 because at 0 it is undefined. So there's a break at 0. The vertical asymptote x equal to 0. So we cannot have anything there. Right. Inflection point. Inflection point is where x equal to 3 and y equal to 10 over 9. So we have one inflection point here. Right. So that's what we have. Now, finally, we need to graph or sketch the function. So we need to put all the first and the second derivative information together. So I'm going to put in the chart like this. I still have a number line. And this is just a summary of what we have for the first and the second derivative. So we have the first derivative, second derivative, and the number line is still the same thing. We don't do any test point here because we already test everything. Right. Now, on the points, now we need to see 2 pages. Right. Now on the points, I will write this in purple. Right. So we have, for the first derivative, we have 0 and 2. And on the second derivative, we have 0 and 3. So we're going to put all of those numbers in. 0, 2, and 3. And that divides the number lines like that. Now the information. The first derivative, on the first derivative, we have negative when it's less than 0, positive between 0 and 2, and negative when it's greater than 2. On the second derivative, negative when it's less than 0, negative between 0 and 3, and positive when it's greater than 3. Right, we just summarize the derivative, the information for all the derivative. It will be easier to graph. Right. Next, uh, based on those patterns, if it is negative and concave down from from negative infinity to 0, the graph will go like this. Next, if it is increasing, but it is concave down as well, so it will be like that instead. Next is negative and concave down, so more like the first one. And then it is decreasing, but it is concave up, so more like that. Right. So we have those graphs. Now let's find all the important information. First, we have the point, the intercepts. We have 1 and 0. So x-intercept, x equal to 1, y equal to 0. That point. Next, the asymptotes, x equal to 0, vertical asymptote, horizontal asymptote, y equal to 0. So draw the line. Let's draw the dashed line. So purple also. So vertical asymptote, horizontal asymptote. We fix that. The derivative, there's only one maximum, x equal to 2, y equal to 5 over 4. and when x equal to 3, y equal to 10 over 9, kind of like that. Let's zoom in and then we'll see better. We'll turn off that, and now we zoom on the graph. Right, that better. Right, now the first part, from negative infinity to 0, it goes like this, and we have the horizontal asymptote, so it just, and the vertical asymptote, so it goes just like that. Graph. We move the vertical asymptote just like that. Right, next, from 0 to 2, it will go like this, and it have to go through the x-intercept of 0 and 1. So we'll go, and it will hit the maximum at 5 or 4. So next, from 2 to 3, the graph goes like this. And then from 3 to infinity. So that's what we have. So if we want to have a better graph, we just need to plot more points. But from the function derivative and the second derivative, those are what we can and we put all together, and that's what we have.